Okay. Hello everyone, this is the second experiment. The object of this experiment is to determine the wavelength of the sodium light using the Fresnel's biprism. So here is the Fresnel's biprism. This is little thing over here, the little glass sheet. And what we need to do, this is based on the phenomenon of interference of light. So what happens? Basically we have a source of light, and that will pass through a narrow slit that's here, that's the another apparatus. Okay, so through this it will fall onto the biprism. It will make actually two virtual sources, and that will pass through, and ultimately we will see, due to the interference of these two light from the two sources, virtual sources would give rise to the fringes, which could be recorded through this thing. Okay, so obviously you know the formula for the wavelength, that's lambda is equal to beta, that is the fringe width, times 2d, that is the distance between the two coherent sources, and capital D, that is the distance between the slit or the screen, which is here, and the slit, which is here. Okay, so obviously you could see all the instruments. This is the optical bench, the sodium light, the Fresnel biprism placed into this one, the slit, and the micrometer through which we could record and see the fringes. Okay, read the width of the fringe. Okay, and then of course this optical bench also has the scale through which you could record the distance between the screen and the slit. Okay, and here too, and how precisely you could do, in fact you have the scales over here, right, main scale and then the vernier scale. Similarly over here too, you have the main scale and the circular scale. So first of all you need to find the least count of all of them, and you could see, in fact, here for the optical bench you have the 10 vernier division, which equals to 1 millimeter. That means the least count is 1 over 10 millimeter, which is 0.1 millimeter, as you could see over here as well. Similarly over here, in this case 1 millimeter is divided into 100 parts, as you could see it on the circular scale. It has 80, 9, 70, 80, 90, 100 comes here. So these 100 divisions equals to 1 millimeter. So you could say 1 over 100 millimeter is the least count of this experiment. So what we need to do, we need to first form the fringes, which is actually a tricky part, very delicate in fact part, and that is the main thing of this experiment. Once we have the fringes, it's easy in fact to do each and everything. Okay, so what are the conditions for the fringes, good fringes to be formed? The light source must be coherent, which is here. Of course we have the sodium light. The slit width should be narrow, so that the light is quite intense, right? And then of course if all those conditions are satisfied, you will have the fringes over here. So I could see, in fact, let me just try to first form the fringes. Okay, all right, I got the fringes out here. I will record these readings first. Okay, what I will do, I will record the reading of D capital, which is the distance between the screen and the slit, capital D. And then what I need to do, I need to find out the fringe width. And in order to find the fringe width, that the distance between the two successive fringes, I will first record the position of all, I have about 20-30 fringes, so that, because actually these would be quite small. So I would record the position of these fringes, take the difference of maybe 10 fringes, divide by 10, right? And that way I will be able to find the fringe width. And that is what I will do for, say for example, 11th minus 1 fringe is 10 fringes. I will measure the separation of those 10 fringes, divide by 10, that will be giving me the fringe width. And similarly I will 12 minus 2, that separation of 10 fringes again, and so on and so forth. Taking the average will give us the precise values. Okay, so fringes are formed. I could see them through this eyepiece and could in fact move my cross wire through this and through this in fact, and keep recording the value of the location of the fringes on this MSR and VSR. So let me show you some tables. This is the table for the least count of the optical bench, main scale, versier scale to least count, okay, position of micrometer least count, that is what you could also do. And the third thing is what I am talking about. So number of fringe. Which fringe? The main scale, circular scale reading into least count is the micrometer reading for the first fringe, okay. So I will move it, place the first fringe, the fringe number 1, whatever we call it, on using this micrometer on the crossbar, record its reading on the main scale over here and the circular scale over here. Move the second fringe again onto the crossbar using this thing. Again I will record the main scale reading and circular scale reading into this table. Second, third, fourth, 15, 16, about 20 fringes. And then as you could see actually, then I need to do the calculation B minus A. That is 11th minus 1 fringe, 12 minus 2 fringe, that is 10 fringe width of the 10 fringes. Then ultimately I will divide it by 10, that mean separation for 10 fringes. So that will give us the mean. So we will take the mean separation of 10 fringes, divide by 10, that will be the fringe width, right? So this way you had recorded the value of beta. Then 2D, how to measure the distance between the coherent sources. Now you know sources are quite far apart, so we need to sort of converge the sources. And in order to do that, I have a converging lens, which is what I am going to place in without disturbing anything else. So this lens must be placed using this stand. So I'm just going to put this out here. As you could see, I placed it, move it this way, and place the lens out here, okay. So now the lens, let me do it here, it is gone into it, okay. And after setting it, I will adjust this lens in such a way that we only see the two lines which are basically representing two sources separated, right? So we will essentially get two positions, points of inversion. In fact, I'm sorry, looks like I didn't place the lens properly. So we will place it maybe at one position somewhere here. We will get another position maybe somewhere here. In between these two, you need to record the separation of the two sources again through this micrometer, okay, and take the difference between the two. That's D1. Similarly, we need to do the D2. Let me check that reading, that thing here. So first micrometer reading, first image, then the second image. So that's okay. Then D1 is A1 minus A2. So these are A1, this is A2, difference is A1 minus A2. Then second time, again, we should get another, essentially we need to move it here. We will again see the similar thing. And then we need to take again the first image, that is first source through this, and then put another source on the crosswire, read those readings, D2, take the difference. That's going to be D1, D2, and the root D1, D2 is going to be 2D. That is the distance, the separation of the two virtual sources. Okay, so now you know 2D, you know the capital D, and you know the beta, which is the fringe width. So then you know the formula. Formula says that lambda is beta times 2D by D. Just place it over, place the values that you had obtained, the fringe width and the separation between the two sources and the distance between the screen and the fringe screen and the slit. That way you should be able to determine the wavelength of the sodium light through the Fresnel Biprism. So this completes your experiment number 2.